I haven't quite worked out whether these are actually avatars or real people. I think some of them are real people at the moment. Like it might be better than having these podium lights on, which don't do very much. Perhaps they don't hurt. But I don't need them, I guess. Those are real people, for sure. All right, so you maybe get the gist. Let's do something else. Don't know that we need the volume. So as you know, I post all the videos from this. Sometimes once they're posted, I get these emails from YouTube saying there's been a claim against your videos for including content. So we have to be a bit careful about what we include. I think they never take them down because it's educational content, or that's what the mission of these recordings are. And so it's never been a problem in the past, but sometimes Red Bull seemed to be always the one that's come to do it. That's why if you looked at the first video we had with the guys wingsuiting and landing in the plane, I cut that off from the beginning just because I didn't want to have to deal with that. Okay, so welcome to the second week of our class. You might be able to guess exactly what we're talking about from these two videos. What we'll talk about is fluid statics. And just to put this also in perspective of what fluid statics also means, is it can also be fluids which are moving, as in this double glazed window with water present in the gap between it. It's in a bus that sloshes around, but the fact that it's not flowing like in a pipe. It's kind of contained in a container. So it could be, we don't need that. I'll get rid of it. And I think it's that one, right? Is that the right one I got rid of? Maybe not. Well, whatever it is, we don't we want another one. So it can be accelerating. And I guess the one thing that is an indicator of that as well, at least in terms of something that is designed with that in mind, in the little clip we just saw of a decelerating fluid, you see that as it decelerates, it stacks itself up at the front of the window, and as it accelerates, it goes to the back of the window behind you like a bulldozer pushing stuff. And so one manifestation of that is, of course, if you've ever wondered why the oil tanks, which you see coming from the Bakken, which cover this country these days on all the railway lines, actually have a dip here and a head space behind and ahead of them. It's exactly for that. It's so that when you fill it up to the brim here, there's a head space of air here, so that when you accelerate, the fluid moves to the back and it doesn't pop the hatch. And likely, I suppose, decelerating it quickly is probably a bigger problem. If you brake, then the same happens when it rushes all to the front. It doesn't pop the hatch and overflow. And so we see natural manifestations of these kinds of behaviors in the things that we'll talk about. And so what we'll talk about today is fluid statics, but it just means fluids within a container that is not circulating in a specific, significant way, but it includes acceleration. We could go through and do 85 pages of derivations today, but I'm not going to impose that on you. Rather than that, I think we'll do some stuff with me scribbling down some things, and so that's the plan for today. And we've used that format before, and we'll use it today. Didn't mean to do that. Meant to do that. And I mean to do this. Okay. So today we'll talk about fluid statics. I guess it can go to the max. And so this is 2:1, right? Oh, this seems quite thick. And so, as the previous title defined, if we're looking at fluid pressures is what our interest is. So pressure at a point. Is really what we're interested in. And we know that fluids come in two flavors, if you like. They come as liquids, which are incompressible and have a free surface, where we can think of density as basically constant. And they come as gases, where density is not constant. In fact, we know that if we look at the ideal gas law, we basically know that pressure, and I have to be careful how I draw my P's and rho's because they look the same. Pressure is proportional to density. Double the pressure, you double the density. That's not the case for liquids, which are basically incompressible. So those are the two classes of fluids that we'll look at. And so these are what we'll think of as incompressible. And these are compressible. So it's not completely madness in what we do. The two clips you saw were free diving. You go down as deep as you can within, well, the time available. The time available is kind of unknown. It's what's in your breath. It's kind of unknown because by the time you get down to the bottom and you're beat, you've still got to get all the way back to the top again. So it's kind of an interesting sport in that. Not without its risks and not without its fatalities, I think, as well. And the other one was people climbing up in the last stages of Everest, where you're climbing in a gas rather than a liquid. But we also know that if we lose compression in a plane, if a window goes out, then people tend to get sucked out. It happened in the last year. There was a lady sitting next to the window when on a Southwest Airlines plane, the fans shattered in the engine and broke the seal to the cabin, and she was part pulled out. Unfortunately died even though she wasn't fully pulled out. And so we know that there's a differential between cabin pressure, which is maintained close to sea level pressure, and the pressure at 30,000 feet, which is basically the same as Everest. And you might have seen those guys climbing Everest with masks on for oxygen to be able to get up to the top. And so what we might do is we could look at, for instance, at what we'd expect to happen on Everest from where we sit here to where Everest sits at the top. Everest is, I don't know, 29,000 feet and change, which is about, well, 33,000 meters. 33,000 feet is 10,000 meters, but let's call it 10,000 meters because we're SI, of course. Sea level is 0 meters. And so what we could do is we could think about this as a big bucket full of air. And that bucket happens to be 10 to the 4 meters tall. It happens to have some kind of cross-sectional area. And we know that the weight of this bucket of air, if there's no bucket there, we can define as equal to the volume of the bucket multiplied by the density and multiplied by G. I'm not sure whether we ever defined this term here. We call this unit weight, which is in kilonewtons. Units are kilonewtons per meter cubed, which is just 1,000 kilograms times 9.81 meters per second squared. And I guess we know that this is also going to be equal to, the volume is going to be equal just to the area times the height, it's called H, times rho G. And if we know that the force acting up on this has to be a pressure, which has to be equal to the weight divided by the cross-sectional area, then we can also write this as the weight being equal to the product of pressure and area. So if we do that, then this is pressure and area. I love using these different colors. We lose this, and we have pressure being equal to the height times rho G, which is the same as equal to the height times the unit weight of the fluid. Right? So if we wanted to calculate the pressure at this point, maybe if we assume that the pressure here is equal to 0, so there's no pressure acting down, in a vacuum, say, that's probably not true, but let's just take that as an example. Then if we do that, then we can calculate the pressure as being equal to, well, what's the unit weight of air, is equal to the density of air times gravity. Density of air at sea level is something like 1 kilogram per meter cubed. You can look it up in your tables. Gravity is 9.81 meters per second squared. Let's make this 10. So this is that the unit weight of air is something like 10 to the 3 times 10 to the 1, which is 10 to the 4. Oh, sorry. No. Okay, I was thinking it's water. This is 10 to the 3. So this is 10 kilonewtons per meter squared, uppercase N. So the unit weight of air is 9.8 kilonewtons per meter squared. So if we want to calculate what the height is, this height is about 10 to the 4 meters. So the pressure would be equal to 10 to the 4 meters multiplied by 10 kilonewtons per meter cubed. I said squared, but it's cubed, which is equal to 10 to the 5 newtons per meter cubed. This isn't kilonewtons, this is just newtons. 10 newtons per meter cubed. So this is exactly equal to what we called absolute pressure at sea level. Pressure absolute at sea level is about 101 kilopascals, which is basically equal to 10 to the 5 pascals, which is equal to, I guess, roughly equal to, which is 10 to the 5 newtons per meter squared. And that's exactly what we get from looking at a column of air which is 10 kilometers tall. So our assumption that the pressure here is actually not bad, if this is true, because if you go from 10 to the 5 here, it assumes that this is 0. So basically, if you looked at the pressures in this column, the pressure with depth would look something like this. 0 at this point, and this would be 10 to the 5 pascals. Is that me or something else? Okay. So that allows us to be able to figure out exactly what the magnitudes of pressure are at this point. It's not very good, because what we haven't allowed for the fact is that we said that we have two different kinds of fluids. We have fluids which are compressible and those which are incompressible. Compressible means that the density is proportional to pressure. If the pressure is changing throughout this column, then we wouldn't expect the density at this height here to be as high as the density of this height here. The density would be varying. And so we can't just take a bucket of this, which we assume is all the same density, and be able to deal with that. So that's our first thing that we have to deal with. But however, what we have got coming out of this is we have an expression, quite an important expression, and that is that the pressure varies as a function of the depth multiplied by the unit weight. What we could also do is we could take that expression and let's instead couch it in terms of a coordinate system. And the coordinate system that we'll use will be x and y horizontally and z vertically. We'll choose to take z vertically upwards. We'll use a right-handed coordinate system. And if we do that, then we could just replace this value of h with pressure is equal to the unit weight multiplied by z. So if we make this equal to z. We just have to be a little bit careful about where we measure it from. If we measure it from some origin where we know the pressure, we can also write this merely by taking a differential component, a small amount of elevation change, dz, and seeing what the small change in pressure that occurs over that length is. So if you don't like using differential calculus, think of these as buckets. We're going to think of this as a bucket that no longer is a circular section bucket, but is a little square differential cube. And what that allows us to get, is this relationship, which is quite important to us. That is, by just rearranging this, the rate of change of pressure with elevation is equal to the unit weight of fluid. As this is written, that's fine based on this expression, but we will choose to do this in a slightly different way. We've chosen to go down from here to this point here, and this has been a positive h. We're going to choose now to go upwards from this, in which case we merely have a negative sign attached to this, which says that as we go up in the column, because our positive direction is z vertically upwards, that the pressure is going to decrease. So as we increase, this is a constant which is positive. As we increase z, we know pressure is going to decrease. And so to get that to work, we just have to have a minus in front of this, just a sign convention. Okay? So that allows us to be able to figure out exactly what pressures would be. This expression, importantly, is always correct. Always absolutely correct. It's correct independent of whether it's incompressible, which it works absolutely for, or compressible. It also works for that. It doesn't work here because we've assumed that the density is constant, and that's not really the case, and that's our assumption. That's our problem, if you like, in doing that. So that's the first step. So we know that we can figure out exactly how pressures change. If we assume that the density is constant, then it would always look like this. I suppose if we assumed that the density is not constant, it would look different. And how different would it look? You could imagine it might look like this. Or I suppose you could imagine that it might look like this. I suppose this would be a fluid where the density at the top is lighter than the other. In other words, the pressure is not changing very much as you go down in depth. And so this would be the one that would be our air, right? High elevations, the density is much less than at sea level, and therefore the distribution here is this. So this difference between an incompressible fluid in blue and a compressible fluid in green is the crux of what we're dealing with between these two fluids. But, to repeat, this is absolutely correct for both of those fluids. Absolutely correct. And I suppose this would be a strange fluid that would be something like an ideal gas law that would be 1 over rho RT, right? At low pressures, the density is high. At high pressures, the density is low. It doesn't exist, I don't think. Anyway, so we need to be aware of this. So this is the one that is the proper one. Okay? So coming back to the idea then that we had before, that we could look at fluids which might be accelerating, then let's try and generalize that. So this is the bus window that has a fluid trapped in it, and or the train cars, the Procore train cars carrying back and crude across the country. All right. So all right. So now what we're going to do, this is going to take the place of 10 pages of derivations. We're going to do it in basically one page. Yawning? Can you believe it? Yawning? So instead of our circular section bucket, which is the height of Everest, we'll draw a differential cube. With that differential cube, we'll define a coordinate system, what we refer to as the right-handed coordinate system. Thumb is X, first finger is Y, second finger, third finger, not sure what it is Z. And so just by convention, it's kind of a mechanics convention. Z is positive upwards. And this is exactly the same as the container we had before, no different. It has some kind of weight to it, it has an area, and we can figure out exactly how the fluid pressure changes as we go along the depth of it. But what we will do is we will define those components. So we have acting downwards, we have its weight, equal W. We'll have acting upwards on this face a fluid pressure, and correspondingly on the bottom face fluid pressure. We'll call this P. We'll call this height, instead of Z or H we called before, we'll call it dz. We don't have to define these other dimensions, but this would be the distance in the y direction, and likewise in x, but we don't need that. We'll assume that the area of this face is A. I won't color it in, but you get the idea here. And do we need anything else? Oh yes, the important thing. We'll assume that we have an acceleration that's applied to this. We'll assume that it's accelerating upwards at some AZ. So in other words, we're in an elevator, you press the button, zoop, you go up. And we'll do that because we're interested in how fluid pressures change vertically within our section. And the final behavior that we have is that on this top face here, let me do that again. So let me get rid of this. Oh no. What an idiot. Is that on this face here, all I needed to do was change the direction of the arrow, that this is another fluid pressure that's acting, but it's plus an increment of fluid pressure. And so as you go from this point here to this point here, pressure changes. It changes by some small amount dP. But let's also multiply that by 1. And you can see immediately we've done nothing but multiply it by 1. And it says that if we know how pressure changes with height, and we multiply it by the length at which we travel over that height, we can calculate what that small change in pressure is. It's doing nothing more than that. So that's what we're attempting to do. We have our best friend, which is Newton's second law. If we talked about prerequisites, I said I don't care about whether you have physics 212 or not, as long as you know what Newton's second law is and can act on it, that's okay. This, of course, has three components. One of these components is the force that's applied in the z direction has to equal the mass multiplied by the acceleration in that z direction. So we have, this has three components. If we wrote it out in longhand, it would be fx, fy, and fz with the appropriate accelerations. We're only interested in this one. And so what we could do is we can sum the forces are that are acting on this system. And so let's start on this bottom face that's right here. So what do we have? We have pressure that's acting multiplied by the area of that face. That's a force, right? Pressure times area. It's in the positive z direction, so it's positive. We have acting down on here a pressure which is equal to pressure plus the change in pressure with elevation times elevation. Again, a pressure multiplied by an area is a force. And we have this acting downwards, which again is negative, because it's acting down against the direction of this. And it's going to be equal to rho times g, which is the unit weight of the fluid, multiplied by its volume of this differential cube. And that's going to be equal to the mass times the acceleration in the z direction. So this is an equal sign, so if you want to differentiate between these two areas, this is basically it. What else do we know? We know that the area is given. We know that the volume is going to be equal to the area multiplied by dz. Right? This height here multiplied by the area of this cube. And so presumably we can, let's use a funky color, and this is going to be equal to area dz, and so is this. So if we write this out in longhand, well, we can make life easier for ourselves first. We recognize that pressure times area and pressure times area cancel out. I guess this pressure doesn't cancel out, but these two do. And so we could write this merely as minus rate of change of pressure with elevation times area times dz, these two terms here, minus, I'm going to write it as this term here is also unit weight of water, or unit weight of the fluid, times area times dz, and you see where this is going, is equal to the unit weight, again, of the fluid. This, again, is area dz. And actually, this is wrong, isn't it? Because this term should not be there. This g should not be there, because this is the acceleration. So this is the acceleration due to gravity, which takes place unit weight. This is the acceleration due to going up in the elevator. So this is the acceleration it feels, not gravity anymore. And so if we rearrange this, we end up with an expression which I'll write out in longhand, which is divide through both sides by volume, which is what this is exactly. And we end up in the z direction with an expression which is minus, it should really be a partial derivative, let's not worry about that. That's why I'll just switch to this. Zero. Sometimes maybe it's better for me to write it, whoops. just for homogeneity's purposes, I'm just going to write this as rho g. It's clearly also equal to unit weight. Right? So that's it. So that's an expression. If we did this in each of the other coordinate directions, and let's do it in reverse order. So if we did this now in the direction y, so in other words, we could resolve this now in this direction, we would come up with something that looks quite similar. It would be equal to in other words, if we apply an acceleration to this, which is in this direction. So this means that the pressure on the back face and the front face, there's a pressure gradient across it, just like there was top and bottom. But now we're looking at resolving forces in the y direction, and y, of course, is orthogonal to gravity. So it doesn't feel gravity at all. So the component of gravity which acts in the direction of y is 0, because it's 90 degrees. And so that's why this term is 0. But it's accelerating in the positive y direction, just like the bus and the window, and therefore we get this. And just by commutation, I guess, in the x direction, rate of change of pressure in x minus 0 minus rho ax is equal to 0. And of course, the acceleration in the x direction, is it for me? I don't care about that stuff. Is that this represents these independent accelerations. Going up in an elevator, this is what you feel. If you're going upwards in an elevator, AZ is positive. If you're going down in an elevator, then you're accelerating downwards, then AZ is negative. And so the sign convention holds. And so actually, you should be thankful to me. There could be 10 pages of note derivations in the notes, but we've got through this. So these are important expressions. We won't use them until the end of next week in this form, but we will use them today in the other forms we have. You'll notice straight away, if we take this expression and we ignore the fact that we have accelerations, if we put these accelerations equal to 0, then we get a few interesting relationships. From the first one, we get that dp dz is equal to minus unit weight. And from the other two, we get dp dy is equal to 0, which is also equal to the change in pressure in the x direction. So these are quite important relationships. We don't get from this, but which is also true, is that the pressure in the x direction is equal to the pressure in the y direction, which is equal to the pressure in the z direction. We didn't define pressures in different directions here, but that is true. It doesn't come out of these relationships, but basically saying that the pressure acting on my head is the same in all directions in this static fluid which we find ourselves in. These are quite important relationships. Well, this isn't so important because we already defined it, right? So we have that. And we've said that this is always true irrespective of whether it's a compressible fluid or an incompressible fluid. This is a relationship which we've actually used already as well. You might remember, if you're here on Friday, that at the end of class, we talked about the idea of a capillary tube. And if you have a fluid which you put a capillary tube into it, and it's a wetting fluid, it will rise within the capillary tube some height h. If it's mercury, if you looked at the notes also, we didn't really talk about it, but if it's a non-wetting fluid, then it would look the opposite and look like this. This would be mercury in glass. This would be water in glass. But what we did was we said that we could take this tube and we could basically cut it off here and make a free body diagram which was basically the height of this thing here. How could we do that? Well, what we did was we went from this point here, and we went to this point here, and said that the pressure here has to be atmospheric. This is P atmosphere. By definition, this is P atmosphere. We didn't give a reason for it, but this is the reason for this, and that is that, I guess you get it from this, since we're not going up or down in elevation, then the pressure here has to be the same as this. But also, since we're going horizontally, we're going from this point here to this point here, say in the x direction, there is no change in pressure as we go horizontally. So the reason for this was basically this expression here. And this means that as you go horizontally in a fluid, you'll be at the same pressure. So if you want to put a foundation in for a house, what you can do is you can take some Tygon tube or a hose pipe, fill it with water, you get the elevation of the water this side, the elevation of the water to the other side is exactly the same. This is a manifestation of this principle, is that it's atmospheric on the surface of the water on your left side and on your right side. So it's no different than that. Okay? So that's quite an important expression for us to deal with. So the other thing that we said we'd do was that we're interested in pressure at a point. And so we said that this also defines the behavior at that point. But of course, clear from this is that the pressure at a point isn't a function only of where we are at the point, it's from everything else that's around us and this stack of fluid that's sitting above us. And so if we want to do that, then we basically have to do what we've done here, but translate it into what our system will look like. And so the easiest way for us to do that is to do it, well, let's do it, I don't know why it's done that. Let's do it for a incompressible fluid. And we've really already done it, right? We've basically said this. This is negative z direction. This is pressure. We know from what we've said about our container what the pressures should look like as we go down through this. We know they're going to look, if you drew a pressure prism, it would look like this, right? These would be the pressures acting as we go down. And so it's no difference in this, is that if you think about it, if we want to get the pressure here at some elevation Z1 relative to Z0, where the pressure will be P1 relative to P0, then the definition, if you like, of these little components, these are just similar triangles. We said that dP, the rate of change of pressure with depth, is equal to minus unit weight. This is equal to dP. This is equal to the change in elevation. And this is just equal to this. So this should be unit weight, and this is 1. That's all this expression means. It means that the rate of change of pressure as you go down is controlled by some property. This property is unit weight. It has units of newtons per meter cubed in SI, and we can find out exactly what the pressure is at a point based on that. We can find out what the pressure is at a point just by rearranging this as dP is equal to minus unit weight dz. We can integrate it between pressure P0 to P1, and and elevation Z0 to Z1. If the fluid is incompressible, then we can take this outside because it's constant. And if we do the integration, it is just pressure evaluated at P1 minus P0, integration limits, minus unit weight, Z Z1, Z0. Substitute the limits. P1 minus P0 is equal to minus unit weight Z1 minus Z0. And so that means if we know the magnitude of the pressure at this point, if we're sitting on top of a swimming pool, then the fluid pressure is atmospheric that's around us. We take that atmospheric, if we're working gauge pressure, as 0. And therefore, we can just rearrange this expression in terms of that. So we end up with minus P0 is equal to minus P1 minus unit weight Z1 minus Z0. Hopefully this works out in terms of the sign convention. We would prefer to do this in positive terms. Let me just use a different color. And so P, I didn't want to do that, did I? I wanted P1. So let's do it for P1. If we do it for P1, it's just equal to minus unit weight Z1 minus Z0. And we subtract off P0, which is plus P0. And then if this is atmospheric, then P0 is equal to 0 in this case. And the rest is that P1 is equal to minus unit weight. Z1 is more negative than this one, and so if we think of this as just being a positive number here, which is h, the difference between those, this gives us and that's kind of the expression that we'll use. So you just have to be mindful of the sign convention, the fact that Z1 minus Z2, Z0 is negative because this is a more negative number than this, right? Because our positive Z is in the upwards direction. Always the convention for us. X, Y, and Z in terms of this, right? Right? So you can always use that. So this is for an incompressible fluid. So for a compressible fluid, is anyone red-green colorblind, by the way? I guess I should be mindful of that. He says, but doesn't look up. All right. So, and of course, this is a synonym for a liquid. We made this point before that for compressible fluid, this would be the trail that we get. This is still going to be the case, that this is going to be 1 over the unit weight, but it's going to change as you go down through it. The density or the unit weight changes as you go down through the fluid. And so we have to allow for that particular circumstance. And so for a compressible fluid, then we start off with our same relationship. I guess we could maybe draw a picture quickly. Not doing a very good job of this. It's going to look like this. This is going to be 1. This is unit weight. This is also pressure versus elevation. This is also dP, and this is also dZ, instead of drawing them as separate components. But the essential difference is this. The pressure change with elevation that we have is now equal to minus the unit weight, which we said always is true, which is equal to minus gravitational acceleration by density. We know that pressure for the ideal gas law is equal to density, absolute pressure, density, gas constant, and absolute temperature. So in other words, if we rearrange this, density is going to be equal to pressure over RT. And so what we could do is we could substitute that into here, in which case we would have dP dz is equal to minus gravity times pressure over rho over R, gas constant times time. We want to be able to integrate from one location at Z0 to Z1 to get from P0 to P1 once again. And so we'll do the same as we did before. We'll split these terms and write it in terms of pressure is equal to minus G 1 over RT. But pressure is a function here, so we have to divide to get that on the same side, and we can put this on the other side. So we've just manipulated this equation, we haven't done anything to it. So now what we can do is we can integrate between pressure at the surface or some location we know and the pressure we'd like to find out. We'd like to do it between places where we know the elevation at Z0 and Z1. Gas constant and temperature, let's assume they don't change. Gravity is the gravity on the planet. And if we do that integration, we get what? We get log P evaluated between those two locations of P0 and P1, and we get minus G over RT evaluated between Z0 and Z1. If we exponentiate that, then we know that e to the log x is just equal to x. If you think back in your mind as to what that is. So you exponentiate both sides. And of course this log p minus log, this becomes log p1 minus log p0, which is the same as, well, it would be log p1 over p0. So let's not exponentiate it first. And this is minus G over RT, Z1 minus Z0. If we integrate and make the substitutions. And if now we exponentiate this, we end up with P1 over P0 is equal to the exponential of this whole term, minus G, the elevation change, which we have to be mindful of doing the right sign convention, divided by the gas constant. And so if we want to just rearrange that, the pressure at point 1 is equal to our reference pressure. I'm just going to write out the same expression, minus gravity multiplied by the elevation difference with the right sign attached to it, divided by the gas constant for that particular gas, temperature. And I suppose all that we should be careful about is that this is the absolute temperature, which we assumed is constant, and these have to be absolute pressures, I think. It's a ratio, so I'm not sure, but I think they do have to be the absolute pressures. And that allows us to be able to get our final behavior. And so basically what that expression would give you is a curve that would look like this. It would give us your steepest descent as you come down. It would get smaller and smaller. And I suppose one way to think about this would be that often we have a gas, which we have here. If you're at the swimming pool, you have a gas sitting on top of water. So if you're sitting at the swimming pool, and this is you sitting here, if you looked at this same graph that we've been drawing of pressure versus elevation, and this is gas and this is liquid, then what you would see, I suppose, would be a curve that looks a bit like this in the gas. In terms of absolute pressures, this would be 101 kilopascals, which is atmospheric sea level. This would be a very small number up here. And within the water, it would start off at this, and it would look like this. Again, if we do our little diagram of this is Z, this is dz dp, and this is 1, and this is unit weight, and indeed this is also 1, and this is unit weight. Whoops. But this is the unit weight of the gas, and this is the unit weight of the liquid. And we know that the density of air is something like 1 kilogram per meter cubed. And we know that the density of water is something like 1,000 kilograms per meter cubed. Unit weights are proportional to these, right? They're just multiplied by the same gravity we feel. So the slope of this here would be 1,000th of this. So if we really drew this to scale, it would physically basically look like this. This would be to scale. Because the density is 1,000 times greater. So we said we set out to define pressures at a point. Pressures at a point, by definition, rely on the conditions that surround them. And to get the pressure at the point we have to know something about the pressures above us. And that's why atmospheric pressure is 101 kilopascals, because it's all the air that exists before it becomes a vacuum of space. Gases are compressible, and therefore density changes with pressure and depth. Liquids are functionally incompressible, and therefore constant and a bit easier. If we know what those magnitudes are, we can calculate exactly what the pressure is at a point by knowing the column around us. That's basically the message today. Okay?